In this review video, we'll work through a set of real exam-style Calculus 1 problems on derivative applications. These are the same types of problems I used to give my university students to review for their exams, and the examples come directly from my Calculus 1 course videos, just the problem-solving portion without the lecture, so you can stay focused on the examples. You can also download the free PDF of all the practice problems on my website, understandthemath.com. Let's get started. We're going to go over a related rates problem that involves the filling of a conical tank. We are told that water is being pumped into an inverted conical tank. I have that picture down here in the diagram so you can see what it looks like. And the water is being pumped in at a rate of 2 meters cubed per minute. We're told that the tank has a height of 6 meters and a base radius of 4 meters. We want to find out how fast is the water level rising when the water is 2 meters deep. Let's now write down what we're given in this problem. We are told that the water is being pumped into the tank at a rate of 2 meters cubed per minute. So that means the rate of change of the volume is equal to 2 meters cubed per minute. And that's positive because water is being pumped in. We're told that the tank has a height of 6 meters. So we'll say H is 6 meters. And then a base radius of 4 meters. So R is 4 meters. And let's put that the radius is 4 meters. And then the height of the tank is 6 meters. Now let's look at what we have to find. We want to find how fast is the water level rising. So when the water is rising, the height of the water is changing. So we want to find dH dt when we're told the water is 2 meters deep. So that means the height is 2 meters. Now we need to think about an equation. We need to find an equation that is going to relate the volume of our conical tank to our height. That formula is the volume is 1/3 pi r squared h. Let's now look at this equation that we just wrote down. Our equation has a volume in it. It has a radius and it has a height. We want to find dH dt. We are given dV dt, but we are not given any information about dr dt. So what we have to do is we have to put r in terms of h. And the only way that we know how to do that is to use similar triangles. So I am going to take just the cross section here of our cone. We were given that the radius is 4 and the height is 6. Now let's think about some water being pumped in. Let's say that this is how much water we have. So we can call this the radius and then this part here the height. We have then two similar triangles. Here's the first one, where we have radius 4, height 6. And then our second one, we have a radius and a height. And they share common angles, so we can use what's called similar triangles. Similar triangles tell us that the ratio of the size of the conical tank, 4/6, is equal to the ratio of the radius to the height. We can then solve for r, so we find that r is equal to 4/6 times h, which is 2/3 times h. Let me go ahead and highlight that because that's what we're going to plug into our formula. Our formula is V is equal to 1/3 pi r squared h. Now we're going to substitute in that r is 2/3 h. So we have 1/3 pi, 2/3 h. That gets squared times h. Our volume then is 2 squared, which is 4. And then we have 3 times 3 times 3, which is 27. So we have a 4/27 pi h cubed. Now we can take the derivative. We have dv dt on the left, and on the right, we have 4/27 pi times 3h squared times dh dt. Let's go ahead and cancel that 3 out. This then is 4/9 pi h squared dh dt. Now let's think about what we want to find. Let's go back up here. We want to find dh dt. So I am going to go ahead and highlight dh dt. That's what we want to solve for. So we can say that dh dt is going to be 9 times dv dt, all divided by 4 pi h squared. We want to find the rate of change of the height when our height is 2 meters. So this is 9, and then dv dt, let's go back up. It is 2 meters cubed per minute. 2 meters cubed per minute. And we divide that by 4 times pi times 2 meters squared. It's really important to put units in at this point so that you know what the units for your final answer are going to be. 9 times 2 is 18. And then in our denominator, we have 2 squared, which is 4, times 4, which is 16. So we have a 16 pi. And then our units are going to be meters per minute. We can divide both the numerator and the denominator by 2. So this is 9/8 pi meters per minute. This tells us that our water level is rising at a rate of 9/8 pi meters per minute. Let's now look at a related rates problem that involves the tip of a shadow moving. We are told that a street light is mounted at the top of a 15-foot tall pole. I put a diagram down here so that you can visualize what this looks like. We're told that a person 6 feet tall walks away from the pole along a straight path at a speed of 4 feet per second. We want to find how fast is the tip of the person's shadow moving when the person is 30 feet from the pole. What we're going to do first is look at our diagram and put some variables in there, and then we'll write down what we're given, what we need to find, and then the equation that relates those two. We're told that the street light is on top of a 15-foot pole, so we'll mark this length as 15. And then we have a person that is 6 feet tall, so we'll label this as 6, and they are walking away from the pole. So let's just make an arrow like this so we can see the direction that they're walking. And they walk away from the pole at a speed of 4 feet per second. So that means we need to set a distance here equal to x, because the x dt will be the speed that the person is walking. We want to then find how fast is the tip of the person's shadow moving. This right here is the tip of the shadow, and we want to see how fast that's moving, so we need to assign a distance to this, and I'm just going to label that L. So let's say here that x is the distance from the person to the pole, And then L is our distance from the shadow, or the tip of the shadow, to the pole. Now let's go ahead and let's put down what we are given. We are told that the person walks away from the pole at a speed of 4 feet per second. So we can now say that dx dt is equal to 4 feet per second. And we want to find how fast the tip of the person's shadow is moving. So that is going to be dl dt. And we want to find that when the person is 30 feet from the pole. So that is when x is 30 feet. Now what we need to do is we need to find an equation that relates x to L. We are going to use what's called similar triangles to get this relationship. I'm going to go ahead and copy down our big triangle. And let's go ahead and let's label this. We have this side is 15, and this distance is L. And now we're going to have a smaller triangle, and that's going to be the height of the person, and then this length right here. We're told that the person is 6 feet, so we can label that as 6. And then now we have to find this distance right here. So let's go back over here to our picture, and I want to highlight this distance right here. That distance is this distance, and that is going to be L minus x. So let's come down here and let's write down the equation for our similar triangles. We have the ratio of 15 is to L as 6 is to L minus x. Now what we're going to do is cross multiply. So we have 15 times L minus x is equal to 6L. So that is 15L minus 15x is equal to 6L. So if we keep the L's on the left, we're going to have 15 minus 6, so that is 9L, and we get a 15x on the right. And we want to find dl dt, so let's solve for L. So this gives us that L is 15 over 9x. And let's see, we can divide 3 into both of those, so we get 5 over 3x. Similar triangles are hard, but once you have it, the equation is actually pretty simple. So we end up with the equation L is equal to 5 over 3 times x. Let's go back up here and see what we want to find. We want to find dl dt. So we are going to take the derivative with respect to time. So we have dl dt is equal to 5 over 3 times dx dt. And we want to find dl dt. Looks like we have to go back up again when x is 30. So x is 30 feet. So this is 5 over 3. Going back up once more, dx dt is 4 feet per second. So this gives us an answer of 20 over 3 feet per second. So we can now say that the tip of the person's shadow is moving at a rate of 20 divided by 3 feet per second. Before we finish, I just want to point out one thing, which I think is kind of unique to this problem. Notice that we did not use x is equal to 30 feet. What that means is the rate of change of the tip of the person's shadow doesn't depend on how far the person is from the pole. That rate stays the same no matter where the person is located. We're now going to walk through 2 examples where we are going to find a linearization. We want to find the linearization L of x of the function at the point x is equal to a. The first function that we are going to be finding the linearization of is f of x is equal to x cubed minus 3x squared plus 4, and we are going to be finding that linearization at the point A is equal to 1. I've written down the formula for the linearization L of x, and it's just f of a times f prime of a times x minus a. So let's start with that. Let's go ahead and let's write down what that formula is. L of x is f of a plus f prime at a times x minus a. When you find a linearization, what you have to actually find is f of a and then f prime of a. Our f of a is equal to f at 1, so we just plug 1 into our function up above, and we have 1 minus 3 plus 4, and that is equal to 2. I'm going to highlight that so we can find it when we need it. Now we need to find f prime of a, so we first have to find f prime of x. So f prime of x, looking at f of x up above, is 3x squared minus 6x. And now f prime of a is just f prime at 1, and that is 3 minus 6, which is minus 3. Now we can write down L of x. L of x is f of a, which is 2, plus f prime of a, which is minus 3, times x minus a, which is x minus 1. Typically, when you find linearizations, you don't multiply this answer out because this form is useful when you use L of x to approximate a function that has an x value that is close to 1. Over here on the right, I have graphed our function f of x and then our linearization L of x. And notice that these two functions are almost identical at the point A is equal to 1. And that's how L of x can be used to approximate f of x. Let's now look at our second example. The function that we're going to be finding the linearization of is f of x is equal to sine x, and we're going to be finding the linearization at the point A is pi over 6. Just like we did with the first example, let's start by writing down our formula. L of x is equal to f of a plus f prime at a times x minus a. Now let's go ahead and substitute in that a is equal to pi over 6. This gives us L of x is equal to f at pi over 6 plus f prime at pi over 6 times x minus pi over 6. F at pi over 6 is just sine of pi over 6, and that is equal to 1/2. And we'll highlight that so we can find it in a minute. Now we need to find f prime at pi over 6, so we first have to find f prime. The derivative of sine is cosine, so f prime is cosine x. Now we can find f prime at pi over 6. That is cosine of pi over 6, which is equal to the square root of 3 over 2. And let's highlight that. Now we can write down L of x. L of x is f at pi over 6, which is 1/2, plus the derivative at pi over 6, which is root 3 over 2, times x minus a, which is just x minus pi over 6. And that's our linearization. I again went ahead and graphed f of x and L of x. And if we zoom in here, you can see that when x is pi over 6, that's this point right here, L of x and f of x are very close to the same value. Let's now look at an application example where we're going to find some error estimates. We're told that the radius of a circular disc is 24 centimeters, and it has a maximum error in measurement of 0.2 centimeters. We want to estimate the maximum error, the relative error, and the percentage error in the calculated area of the disk. Y is equal to f of x is the function that we're going to be calculating the error in. So in our example, this is going to be the area function. The maximum error is given by dy. The relative error is then dy divided by y. And then the percentage error is just the relative error times 100%. I went ahead and drew a circle to represent our circular disk. It has a radius r, and we're going to write down that the area is pi r squared. So we are going to be calculating the error in this area. Let's first find the maximum error. So the maximum error is going to be dA. Taking that derivative, we have 2 pi r times dr. We are told that r is 24 centimeters, and then the maximum error in measurement, that's actually dr, and that is 0.2 centimeters. And now we can find dA. So dA is 2 pi times r, which is 24 centimeters. Make sure to put units in there. And then our dr is 0.2 centimeters. And this is equal to 9.6 pi centimeters squared. When we leave pi in our answer is an exact answer. Now let's find the relative error. That is dA divided by A. dA was 2 pi r dr. I'm just looking right up here for that. And then we divide it by A, which is pi r squared. So one of the r's cancels, the pi's cancel. So we end up with 2 dr in the numerator and then r in the denominator. We have 2 times dr, which is 0.2 centimeters, all divided by r, which is 24 centimeters, which gives us a relative error of 0.0167. The last thing that we need to calculate is the percentage error. So the percentage error is just our relative error, 0.0167 times 100%. So this is just 0.0167 times 100. And that gives us a value of 1.67%. So this calculation tells us that if the error in our radius is 0.2 centimeters, the percentage error in our area is 1.67%. We're going to walk through some examples where we are going to find the critical number of a given function. I've written down a method that we can follow just to make things easier. The first function that we're going to find the critical numbers for is the function f of x is x cubed plus x squared minus x. Our first step is to calculate f prime at x. So let's do that. F prime at x is equal to 3x squared plus 2x minus 1. And then our second step is we're going to set that equal to 0. We can factor this. This is 3x minus 1 and x plus 1. That's equal to 0. And then if we set both of these factors equal to 0, we get that x is equal to 1/3, and we get that x is equal to -1. These two numbers then are our critical numbers. Over here on the right, I have graphed this function just so that you can see what it looks like when we have a critical number. When x is -1, the slope of our curve is equal to 0, and we have what's called a local max. And then when x is 1/3, we also have a slope of 0. And at that point, we have a local min. Let's now look at our second example. In this example, we're given that f of x is equal to x cubed plus x squared plus x. We're going to begin by taking the derivative. F prime at x is equal to 3x squared plus 2x plus 1. And we're going to set this equal to 0. Now we have to factor this. When I look at this, I cannot see an easy way to factor it. So we are going to have to use the quadratic formula. Let me just go ahead and put that over here. The quadratic formula tells us that x is -b plus or minus the square root of b squared minus 4ac, all divided by 2a. Let's see what this gives us. X is equal to -b, so that's -2, plus or minus the square root of b squared, so that's 2 squared, so that's 4, minus 4 times a, which is 3, times c, which is 1, all divided by 2 times a, which is 3. Let's look at this part right here. That is equal to 4 minus 12, which is -8, and that is less than 0. So this tells us that we have no real roots. And whenever we have no real roots, we have no critical numbers. Let's now look at the graph of this function so that we can see what a function looks like when you don't have any critical numbers. Notice that our function is always increasing. The slope of the function is never equal to 0, and there are no max or mins, so there are no critical numbers. We are going to find absolute maximum and minimum values of our function on the given interval. Our first example is the function f of x is equal to x cubed minus 6x squared plus 9x plus 2, and then the closed interval that we're given is from -1 to 2. The first step in our closed interval method is to find the critical numbers. So we're going to start by taking the derivative. Our derivative is going to be 3x squared minus 12x plus 9, and we are going to set that equal to 0. We're going to need to factor this, but notice that there's a 3 common to each term, so let's go ahead and let's pull that out. So this is x squared minus 4x plus 3 is equal to 0, and we can factor this as, let's see, we can have an x minus 1 and then an x minus 3. We set x minus 1 equal to 0, and we get x is equal to 1, and then we set x minus 3 equal to 0, and we get x is equal to 3. X is equal to 1, and x is equal to 3 is a critical number. Our second step is to check if each of these critical numbers is in the interval from -1 to 2. X is equal to 1 is in the interval from -1 to 2, but x is equal to 3 is not in our interval from -1 to 2. Let's highlight this number because that is a number where we're going to potentially have a max or a min. Let's go to step 3. Step 3 says that we have to find the value of f at the critical number in the interval and at the endpoints. So we are going to find f at 1. You just go back up to the original function. Let me go ahead and highlight this in yellow. And we're going to substitute in that x is equal to 1. Notice that we are not substituting it in to that function. Up at the yellow, we have 1 cubed, so that's just 1 minus 6 plus 9 plus 2. Let's see, if we add up the positive terms, we have a 12. So this is 12 minus 6, and we get a value of 6. Let's highlight that because that's one of the numbers we're going to have to compare. Now we need to find our function at each endpoint. So let's compute f at minus 1. Looking back up to the yellow highlight, we have minus 1 cubed, so that's minus 1. And then we have minus 6, minus 9, plus 2. Let's see, we have a minus 10 minus 6, so that's minus 16 plus 2, gives us minus 14. That's a number that we have to compare. And now we have one more. Our other endpoint, which is at 2. So f at 2 is 2 cubed, which is 8, minus 6 times 2 squared, which is 4, plus 2 times 9, which is 18, plus 2. So let's see, this is 28 minus 24, so that is 4. Now our fourth step is to look at the 3 values that we got in step 3 and find the largest one and the smallest one. The largest value is 6, so we are going to say that we have an absolute max equal to 6 at the point x is equal to 1. And now let's look at our pink values and see the smallest one. The smallest one is minus 14, so we have an absolute min equal to minus 14 at x is equal to minus 1. And those are our answers to our problem. Before we move on, I want to show you what the graph of this function looks like. It's graphed over here on the right. Notice that when x is equal to negative 1, that's our left-hand endpoint, we have an absolute min. And then when x is equal to 1, that was one of our critical numbers, we have an absolute max. And you can see that the derivative is equal to 0 because we have a horizontal tangent. We are asked to verify that a function satisfies the 3 hypotheses of Rolle's theorem on the given interval. Then we are to find all numbers C that satisfy the conclusion of Rolle's theorem. The function f of x that we're given is x cubed minus 3x squared plus 2x plus 1, and the closed interval that we're given is from 0 to 2. I've graphed this function over here on the right, and when we get done with this problem, we're going to come back to that graph and see how our answers that we're going to get make sense. The first hypothesis of Rolle's theorem is that f is continuous on the closed interval from a to b. Our function f of x satisfies this because f of x is a polynomial, and all polynomials are continuous. So we say that f of x is a polynomial, so it is continuous on the closed interval from 0 to 2. Our second hypothesis says that f is differentiable on the open interval. Let's go ahead and let's take the derivative. F prime of x is 3x squared minus 6x plus 2. Notice that f prime of x is also a polynomial, so let's write that down. F prime of x is a polynomial, So we can conclude that it, meaning f of x, is differentiable. And here's where we have to be careful. It is differentiable on the open interval. It's always continuous on the closed interval and differentiable on an open interval. Let's now look at our third hypothesis. This says that f of a is equal to f of b. That just means the function is going to be the same value at the endpoints. So we are going to have to find the function at each endpoint. Our first endpoint, x is 0, so we're going to plug in x is equal to 0. And looking back up here, let me go ahead and highlight it so you can see where we're looking. We're going to substitute x is equal to 0 into that, and you can see that we get 1. Now we're going to do the same thing for x is equal to 2. This is going to be 2 cubed, which is 8, minus 3 times 2 squared, which is 4, plus 4 plus 1. Let's see. This is 13 minus 12, and it is equal to 1. So that hypothesis holds because the function has the same value at each endpoint. Now what we need to do is we want to find all numbers C that satisfy the conclusion of Rolle's theorem. And the conclusion of Rolle's theorem is that there is a point C between A and B where f prime at C is equal to 0. So what we have to do is we have to find the derivative, which we've actually already found in step 2, and we have to set it equal to 0. So let's just copy it down again. F prime of x is 3x squared minus 6x plus 2, and we set that equal to 0. Now, when I look at this, we need to factor it, but there is no way that we can factor that unless we use the quadratic formula. So let me just remind you what the quadratic formula is. I always think it helps to write it down. X is minus b plus or minus the square root of b squared minus 4ac, all divided by 2a. Let's now apply that. We have x is equal to negative b, so that's a minus 6, plus or minus the square root of b squared, so that's minus 6 squared, minus 4 times a, which is 3, and then c, which is 2. And we divide all of this by 2 times a, which is 2 times 3. Let's now see what we get. This is 6 plus or minus the square root of 36 minus 24, all divided by 6. So this is 6 plus or minus the square root. Let's see, 36 minus 24, that is 12, all divided by 6. When we take the square root of 12, that's just the square root of 4 times 3. So we can pull out the 4 as a 2. And we get x is equal to 6 plus or minus 2 square root of 3, all divided by 6. So this is 1 plus or minus root 3 divided by 3. Now what we have to do is we have to determine if these points are in our interval from 0 to 2. Let's look at these individually. The first one is x is 1 plus root 3 over 3. Putting that into our calculator, we get approximately 1.577. That is between 0 and 2, so that one will work. Now let's look at the second one. X is 1 minus root 3 over 3. That is approximately 0.423. So that one also works. It is between 0 and 2. So we can write down that C is equal to 1 plus root 3 over 3, and C is equal to 1 minus root 3 over 3. Let's go ahead and let's highlight those answers. There's our first one, and there is our second one. So this tells us that at those 2 points, our function is going to have a slope of 0. Let's go back up to our graph at the top, and let's see if that's true. Let's first look at the value of our function at the endpoints. At 0, we have a function value of this, and here is our function value at 2. You can see that they are the same points. And then at this point, we have a horizontal tangent, and at this point, we have a horizontal tangent. This point is 1 minus root 3 over 3, and then this point over here is 1 plus root 3 over 3. I think it always helps to graph the function just so that you can really understand what it is you are calculating. I make all my graphs on Desmos. It's a free graphing calculator that is really easy to use, and I highly recommend it. We are going to walk through some examples that require the use of the mean value theorem. Let's look at our first example. We are asked to verify that the function satisfies the hypotheses of the mean value theorem on the given interval. Then we are asked to find all numbers C that satisfy the conclusion of the mean value theorem. The function f of x that we're given is x cubed plus x squared plus 1, and the closed interval is from -1 to 1. I put a graph of our function over here on the right, and we're going to look back at this graph after we finish all of our calculations. The first hypothesis of the mean value theorem is that our function is continuous on the closed interval. Our function, f of x, is a polynomial, so we can write down that f of x is a polynomial. So it is continuous on the closed interval from -1 to 1. Every polynomial is continuous. Let's now look at the second hypothesis. F is differentiable on the open interval from a to b. It is a fact that all polynomials are differentiable, but let's just go ahead and take the derivative. We're going to need it later anyway. F prime of x is going to be equal to 3x squared plus 2x. Notice that the derivative is a polynomial, so we can say that f prime of x is a polynomial. So f of x is differentiable on the open interval from -1 to 1. Now what we have to do is find all numbers C, here's C right here, that satisfy the conclusion of the mean value theorem. The conclusion tells us that the derivative at some point C is going to be f of b minus f of a over b minus a. That's just saying that the instantaneous rate of change, which is f prime of c, is equal to the average rate of change, which is the f of b minus f of a over b minus a. Let's start by writing down our function. We have f of x is x cubed plus x squared plus 1, and then we already found the derivative. That was 3x squared plus 2x. Now we're going to set the derivative, 3x squared plus 2x equal to f at 1 minus f at -1, all divided by 1 minus -1. We have lots of negatives going on there. Let's just go ahead and let's work on the right-hand side. F of 1 is going to be 1 plus 1 plus 1. And then we're going to subtract off f at -1. In case you're wondering, I'm looking right here for f of x. So this is going to be minus 1 plus 1 plus 1. And then we're going to divide all of this by 2. Let's see what this gives us. This is 3 minus 1 over 2, which is 2 over 2. So this actually is just equal to 1. We now need to solve the equation 3x squared plus 2x is equal to 1. Let's pull the 1 to the left, so we have 3x squared plus 2x minus 1 is 0. We can factor this. Let's see, we're going to put a 3x here and an x here. So this needs to be a plus 1, and that can be a negative 1. That works. So we end up with x is 1/3, and x is equal to negative 1. The conclusion of the mean value theorem says that f prime of c is f of b minus f of a over b minus a, but that is only valid in the open interval. So let's notice down here that this point is not in the open interval from minus 1 to 1. It is an endpoint. So this point will not work. And this is the point that satisfies the mean value theorem. So our answer is going to be that c is equal to 1/3. Now let's take what we just found and let's go back up to our graph and see if it makes sense. Here is our function value at our left endpoint. That's at negative 1. And then at 1, let's see, it's up here. That is our function value at our right endpoint. And the mean value theorem tells us that the average rate of change, that's represented by the slope of the secant line, is equal at some point to the instantaneous rate of change. We found the point 1/3, and that's about right here. And you can see that the slope of the tangent line at that point is the same as the slope of the secant line. So the number c that we got is definitely correct. We are going to find the intervals on which f of x is increasing or decreasing. Just to make things easier, I've written down 3 steps that we can follow. We're first going to find the critical numbers, and then we're going to find the value of f prime to the left and right of each of those critical numbers. And then step 3, we can just write down the intervals for increasing. That is when f prime is greater than 0, or decreasing when f prime is less than 0. Let's look at our first example. We're given the function f of x is equal to 3x to the 4th minus 4x cubed minus 12x squared plus 5. The first thing that we're going to do is find the critical numbers. So we're going to start by taking the derivative. F prime of x is equal to 12x cubed minus 12x squared minus 24x. To find the critical numbers, we set that equal to 0. It looks like we can factor out a 12x, and then we're left with x squared minus x minus 2. We can then factor our quadratic. Let's see, we can factor it as x plus 1, and then x minus 2. And then we set all 3 of those terms equal to 0, and we get x is equal to 0, minus 1, and 2. Our second step is to find the values of f prime to the left and right of these 3 numbers. I'm going to highlight f prime because that is what we're going to have to be looking at. Let's now make a number line. This is going to be x, and we're going to put our critical points on it. We have negative 1, we have 0, and then we have 2. The spacing doesn't matter at all. We're now going to be looking at the value of f prime to the left and right of these 3 points. When you're working with a polynomial, the region to the left and the region to the right of all the critical points is determined by the leading term of f prime. The leading term has an x cubed in it, so it is going to be negative when x is negative, and it's going to be positive when x is positive. That just makes it a little bit easier. Now what we have to do is look at values between -1 and 0, and then between 0 and 2. For this part, I think it's easiest if we look at the factored form of f prime, which is this part right here. Over here on the right, I am going to make a table. I'm going to put down x, and then I'm going to put all of the factors that I highlighted in orange. So we have x, x plus 1, and x minus 2. And we are going to be looking to see if those factors are positive or negative. The point that I'm going to choose between -1 and 0 is -1/2. And then -1/2 is negative. -1/2 plus 1 is positive. And then -1/2 minus 2 is negative. Now let's pick a point between 0 and 2. I think the easiest point is 1. So 1 is positive, 1 plus 1 is positive, and then 1 minus 2 is negative. In the region between -1 and 0, we have a negative times a positive times a negative, so that's going to give us a positive. And then in the region between 0 and 2, we have a positive, positive, and a negative, so that is going to be negative. I think before we go to step 3 and write down the intervals for increasing or decreasing, I've always found that it helps to draw an increasing or a decreasing line in each interval. So in our leftmost interval, we have decreasing, then we have increasing, decreasing, and increasing. Now we can just write down the intervals for increasing and decreasing. Our function is decreasing on the interval from -infinity to -1 and on the interval from 0 to 2. And then our function is increasing on the interval from -1 to 0, and then our rightmost interval from 2 to infinity. And we'll go ahead and we'll highlight those answers. Before we go on to the next problem, let's look up here on the right at our graph. Our critical points are the points right here, here, and here. They're the points where our function changes from increasing to decreasing or vice versa. And you can see on the graph that our function is decreasing in this interval and in this interval, and then it's increasing in this interval and in that interval, just like we calculated. Now let's look at our second example. We're given the function f of x is equal to 2 plus the quantity x minus 5 cubed. Just like we did with our first example, we are going to start by taking the derivative. We have f prime at x is equal to 3 times x minus 5 squared, and then the derivative of what's inside is just 1. And we set that equal to 0, and we get a value x is equal to 5. For step 2, we are going to draw our number line. And this time we only have one point to put on it, and that is that x is equal to 5. Now we need to find the value of f prime to the left and right of 5. Let's go ahead and highlight this because that's what we have to look at. Notice that that is a function that is squared, so it is always positive. So we're going to have a positive value for f prime to the left and a positive value to the right. So our function is increasing and increasing. One thing we have to keep in mind though, at 5, the derivative is equal to 0, so the function has a horizontal tangent and is not increasing there. So for our answer for part 3, we have to say that our function is increasing on minus infinity to 5 and from 5 to infinity. And we have to leave out the 0.5. Here's our answer then. And before we go on to the next problem, let's look at our graph over here on the right. This is our critical point when x is equal to 5. You can see that there is a horizontal tangent there. And then to the left and right of that point, our function is increasing. We are going to use the first derivative test to find the local maximum and minimum values of f of x. Just to make things easier, I have written down some steps that we can follow. The first step is to find the critical numbers. The second step is to find the value of f prime to the left and right of each critical number. And then our third step is to just calculate the local maximum. That is going to be where f prime changes from positive to negative. And then find the local minimum. And that is where f prime changes from negative to positive. In our first example, we're given the function f of x is equal to x cubed minus 6x squared plus 5. For our first step, we are going to find the critical values. So we're going to start by taking the derivative. F prime at x is 3x squared minus 12x, and then we set that equal to 0. We can factor out a 3x, so we're left with x minus 4. And this gives us that x is equal to 0 and x is equal to 4. Those are our critical values. In our second step, we are going to take these critical values and we are going to put them on our number line. The nice thing is that spacing doesn't matter. So here's 0 and here is 4. And we are going to be looking at the value of f prime. Let me go ahead and highlight f prime so we can see what to look back at. Because f prime is a polynomial, when we look at the regions to the left and right of our critical numbers, we only have to look at our leading term, which is x squared. That term is positive, so we know that to the left and right, f prime is going to be positive, and then all we have to do is now just pick a point in the middle. I'm going to choose x is equal to 1, and we're going to have to see what f prime is. F prime at 1 is just going to be 3 minus 12, and that is negative. So we're going to put a negative here. And then let's go ahead and let's draw some lines. When f prime is positive, our function is increasing, then it's decreasing, and then it is increasing. Now let's look at our third step. We just have to find the value of the local maximum and local minimum. We are going to have a local maximum at 0. So let's calculate f at 0. Let me highlight this because this is what we're looking back up at to find f of 0. So f of 0 is just 5. Now let's calculate f at 4. That's where our local minimum is going to be. And this is 4 cubed minus 6 times 4 squared, which is 16, plus 5. And that is, let's see, 4 cubed is 64, minus 96 plus 5, and that adds up to be minus 27. So for our answer, we can say that 5 is our local max, and minus 27 is our local min. Before we go on to our next example, let's take a quick look at our graph. Our critical values are here and here. And that's where our function changes from increasing to decreasing, as well as where our local max and mins are. And you can see that right here, at x is equal to 0, we have a local max. And when x is equal to 4, we have a local min. We are going to find the intervals of concavity, and then we're going to find the inflection points for our function f of x. Just to make things easier, I have written down 4 steps that we can follow, and we'll go through these as we walk through our example. For our first example, we have the function f of x is equal to x to the 4th minus 4x cubed. Our first step is going to be to find f double prime, set it equal to 0, and solve for x. F prime of x is 4x cubed minus 12x squared, and then f double prime of x is 12x squared minus 24x. We are going to set that equal to 0, and we're going to solve for x. Looks like we can pull out a 12x, so we're left with x minus 2. And this gives us that x is equal to 0 and x is equal to 2. Now let's look up at our second step. We are going to find the value of f double prime to the left and right of each of these values of x. So I think the easiest thing to do is to go ahead and draw a number line. Here's our number line. We're going to put an x there, and we're going to put in the points x is 0 and x is 2. And we're going to be looking at the value of f double prime. So let me highlight f double prime, and that is this value right here. Because f double prime is a polynomial in this region and in this region to the left and right of our critical points, we can just look at the leading term to find the value of f double prime. It is an x squared, so it is positive. So we can say it's positive here and it's positive here. Now all we have to do is pick a point in the middle. I think the easiest point to choose would be that x is equal to 1, so we're going to find f double prime at 1. Looking back up to our formula in yellow, this is 12 minus 24. That is less than 0. Doesn't matter the value, we just need to know if it's positive or negative. And let's put a minus right here. Now let's look back up at our steps and look at step 3. We want to write down the intervals for concave up. That is when the second derivative is positive, or concave down when the second derivative is negative. I think it's easiest if we put a little graph on the number line that we've made. If we have a positive, it's concave up, and then we have concave down, and then we have concave up. Now it's really easy to write our intervals. So for step 3, it is going to be concave up on the intervals from minus infinity to 0 and from 2 to infinity. And then it's going to be concave down on the interval from 0 to 2. And let's go ahead and let's highlight those answers. There's our concave up, and there's our concave down. Now let's go back up and look at step 4. We want to write down the inflection points, and those are just the points where the concavity changes. The concavity changes at 0 and at 2. So this means we need to find the value of our function. Let me go ahead and highlight this in orange at the points 0 and 2. So let's write down number 4. We are going to calculate f at 0. That's just 0, so that's nice. And then f at 2, that is going to be 2 to the 4th minus 4 times 2 cubed. This is 16 minus 4 times 8. So this is 16 minus 32, and that's minus 16. So we can say for f of 0, we have an inflection point equal to 0, 0, and we'll highlight that. And then for x is equal to 2, we have an inflection point equal to 2 minus 16, and we'll highlight that. Before we go on to the next problem, let's look back up here at our graph. We found that we have inflection points at 0 and at 2. Those are those points right there. And then our concavity changes to the left and right of those points. We have concave up in this region, and then we have concave down, and then we have concave up again. In these examples, we are going to use the second derivative test to find the local maximum and minimum values of f of x. I've written down some steps that we can follow. The first step is to find the critical numbers, and then the second step is to find f double prime, and then check if f double prime is positive or negative at our critical numbers. And then step 3 is we just calculate the local max and mins. Let's see how this works. The first function that we're given is a polynomial, and its f of x is equal to x cubed minus 6x squared plus 5. Our first step is to find our critical numbers, so we're going to take the derivative. F prime of x is 3x squared minus 12x. We are going to set this equal to 0. We can factor out a 3x, and we're left with x minus 4. So this gives us that x is equal to 0 and x is equal to 4. Now, in step 2, we are going to find the second derivative. That second derivative is going to be based off of our first derivative, so we're going to differentiate that. So we're going to have a 6x minus 12. Now, we don't set this equal to 0. Instead, we take our critical numbers, that's this number, and we substitute it in for x. So f double prime at 0 is minus 12, and that is less than 0. So that tells us that we are going to have a local max at x is equal to 0. Remember, it's just opposite. If it's less than 0, you have a max. If it's greater than 0, you have a min. Now let's find f double prime at 4. This is 6 times 4, so this is 24 minus 12. That is greater than 0. The value doesn't matter. We're just checking if it's positive or negative. If it's greater than 0, that tells us that we're going to have a local min at x is equal to 4. Now, in step 3, we actually have to find out what the minimum and maximum values are. So we need to go back up to our original function and plug in those x values. We have f at 0. That one's easy. That's just equal to 5. So that tells us that we have a local max equal to 5. And that, of course, is at x is equal to 0. Now let's plug in 4. This is going to be a little bit more work. F at 4 is 4 cubed minus 6 times 4 squared plus 5. Let's see. This is 4 cubed is 64 minus 6 times 16 plus 5. So let's see, 64 minus 96 plus 5, that is actually minus 27. So that tells us we have a local min equal to minus 27, and that occurs where x is equal to 4. Let's now walk through some examples so that we can understand how L'Hopital's rule works. We are going to evaluate the following limits. The first limit is the limit of x squared plus x minus 6, all divided by x minus 2 as x approaches 2. The first thing you always want to do when you are evaluating a limit is start by substituting the given value of x, in our case, x is approaching 2, into the expression that you're given. If we substitute x is equal to 2 on the numerator, we get 2 squared, which is 4, plus 2 minus 6, and we divide all of that by 2 minus 2. This is equal to 0 over 0. When we get 0 over 0, we know that we can use L'Hopital's rule. I'm going to put a little LH over here each time I use L'Hopital's rule. L'Hopital's rule tells us that this is equal to the limit as x approaches 2 of the derivative of the numerator, which is 2x plus 1, all divided by the derivative of the denominator, which is 1. Now we go ahead and substitute in that x is 2, and we get 2 times 2 plus 1, all divided by 1, and that gives us an answer of 5. So our limit is equal to 5. Let's now look at our second example. We are given the limit of cosine x minus 1, all divided by x, as x approaches 0. We'll start by substituting in that x is equal to 0. So we have cosine of 0 minus 1, all divided by 0. Cosine of 0 is 1, so we have 1 minus 1 over 0, and we get 0 over 0. This means we can use L'Hopital's rule, and this is equal to the limit as x approaches 0. Now we're going to take the derivative of the numerator. The derivative of cosine is minus sine, so we have a minus sine x, and then derivative of 1 is 0. And the derivative of the denominator is the derivative of x, which is just 1. Now we're going to substitute in that x is equal to 0. So this is minus sine of 0. Sine of 0 is just 0, so we get 0. Here's our example. We are going to evaluate the following limit. Our limit is the limit of sine x times natural log x as x approaches 0 from the right. X is approaching 0 from the right because the natural log is only defined when x is greater than 0. We're going to start by just substituting in that x is approaching 0. So this is sine of 0 from the right times natural log of 0 from the right. Sine of 0 is 0, and then the natural log of 0 from the right is minus infinity. So we get the indeterminate form 0 times infinity. This means that we need to rewrite our function. Let's go ahead and let's do that. We're going to write this as the limit as x approaches 0 from the right. Now we have to decide, do we want to put 1 over sine x in the denominator or 1 over natural log x? 1 over sine x, let me go ahead and write this over here. 1 over sine x is cosecant x. We know how to take that derivative. We also know how to take the derivative of 1 over natural log x, but it's a lot more complicated. So I am going to choose to put the natural log x in the numerator, and then in the denominator, I have 1 divided by sine x. Let's see what this gives us when we let x go to 0 from the right. This is natural log 0 from the right, all over 1 over sine 0 from the right, and this is minus infinity divided by 1 over 0, so we get minus infinity over infinity. And that is the indeterminate form that tells us that we can apply L'Hopital's rule. So that's what we're going to do. I'm going to put a LH over here so that we know we're using L'Hopital's rule. And this gives us the limit as x goes to 0 from the right. Now we're going to take the derivative of natural log x, which is 1 over x. And now we're going to take the derivative of our denominator. Let's just make a note here that this is cosecant x. The derivative of cosecant is minus cosecant x cotangent x. And now we need to know what that limit is. I think the form that our limit is in makes it difficult to evaluate things. So I am going to change this back to be the limit as x goes to 0 from the right of 1 over x on the top. And then I'm going to write cosecant as 1 over sine x. And then let's put in that cotangent is cosine x over sine x. And we're going to rewrite this as the limit as x goes to 0 from the right. We're going to take the minus sine squared x up on top. And then in our denominator, we have an x cosine x. And that's much easier to evaluate. It's really common when you use L'Hopital's rule to have to simplify as you go along. Let's now substitute in that x is approaching 0. Because we don't have the natural log anymore, I am just going to write down 0 instead of 0 from the right. So this is minus sine 0, all divided by 0 times cosine 0. Sine of 0 is 0, and then we have 0 times cosine of 0 is 1. So we get 0 divided by 0, and that is the other indeterminate form that tells us that we can use L'Hopital's rule. So we are going to use L'Hopital's rule again. And let's see what we get. This is the limit as x approaches 0 from the right. We're going to take the derivative of minus sine squared x. We're going to have to use the power rule. So this is minus 2 sine x times cosine x. And then in the denominator, we are going to have to use the product rule because we have one function and a second function. The derivative is our first function times the derivative of our second, and that is a minus sine x. And then we have our second function, cosine x, times the derivative of our first. The derivative of x is 1. Now let's go ahead and let x be equal to 0. So this is minus 2 sine of 0 times cosine 0, all divided by 0 times minus sine 0 plus cosine 0. Sine of 0 is 0, so this is minus 2 times 0 times 1, all divided by 0 plus 1 in our denominator, and this gives us an answer of 0 over 1, which is equal to 0. And that's our final answer. The first limit that we're going to evaluate is the limit of x times e to the 1 over x minus x as x goes to infinity. First thing you always want to do is substitute in what x is. So this is infinity times e to the 1 over infinity minus infinity. This is infinity. 1 over infinity is 0, so we have e to the 0 minus infinity. E to the 0 is 1, so we have infinity minus infinity. This is an indeterminate form, and we now need to put this form into 0 over 0 or infinity over infinity. Notice that with the function that we're given, let me go ahead and highlight this. Can you see that there is an x common to each term? Because of that, we can factor out an x. So let's go ahead and let's do that. This is the limit as x goes to infinity. We're going to factor out an x, and we're left with e to the 1 over x minus 1. Now we want to go ahead and substitute in that x is equal to infinity. So we have infinity times e to the 1 over infinity minus 1. This is infinity. E to the 1 over infinity is e to the 0 minus 1. So this is infinity to the 1 minus 1, which is infinity times 0. This is an indeterminate form. It's not 0 over 0 or infinity over infinity, so we have one more step to do before we can use L'Hopital's rule. What we have to do is rewrite this limit, let's highlight this, in such a way that we get 0 over 0 or infinity over infinity. So we have to take either the x or the e to the 1 over x minus 1 to the denominator. It's going to be a lot easier if we put x in the denominator. So that's what we're going to do. This is the limit as x goes to infinity. We're going to have e to the 1 over x minus 1 in the numerator. And then in the denominator, we're going to have 1 over x. Let's see what that is equal to. We're going to let x go to infinity. So this is e to the 1 over infinity minus 1, all divided by 1 over infinity. 1 over infinity is 0, so this is e to the 0 minus 1, all over 0. So we get 1 minus 1 over 0, and we get 0 over 0. Now, finally, we have a form that we can use L'Hopital's rule. I'm going to put an LH over here so we know that we are using L'Hopital's rule. And now we're going to take the derivative of the numerator and the derivative of the denominator. The derivative of e to the 1 over x minus 1 is e to the 1 over x times the derivative of 1 over x. Let me go over here and let me write down in the left-hand side the derivative of 1 over x. This is equal to minus 1 over x squared. If you haven't memorized that, that might be a good one to memorize. It just makes things go a little bit quicker if you have that memorized. So back to our problem. We had e to the 1 over x. Now we're going to have to multiply by the derivative of 1 over x, which is minus 1 over x squared. And then we have a 1 over x in the denominator, so we're going to write down that derivative, and that is minus 1 over x squared. One thing that is really nice with this problem is that the minus 1 over x squared cancel out, and so we're just left with e to the 1 over x. This is the limit as x goes to infinity, e to the 1 over x. Now we let x go to infinity, so this is e to the 1 over infinity, which is e to the 0, and this is equal to 1, so the value of our limit is equal to 1. In our example, we are going to take the limit of cosine of 3x raised to the 5 over x as x goes to 0. We're going to start by substituting in that x is equal to 0. So this is cosine of 0 to the 5 divided by 0. Cosine of 0 is 1, so this is 1 raised to the 5 over 0. 5 over 0 is infinity. So this is 1 to the infinity. This is an indeterminate power. You feel like it should be 1, and sometimes it is, but oftentimes it isn't. So you have to go through and evaluate it. Let's walk through our steps. Our first step is we're going to take y, and we're going to set it equal to the function that's in our limit. And this is cosine 3x raised to the 5 over x. Our second step is to take the natural log of both sides because that enables us to bring the 5 divided by x out in front. Natural log of y is natural log cosine of 3x raised to the 5 over x. We can rewrite our right-hand side as 5 over x times natural log of cosine of 3x. Now in step 3, we're going to take the limit. We were given that our limit is x is approaching 0. So we're going to take the limit as x goes to 0 of both sides, natural log of y, and then the limit as x goes to 0, 5 natural log cosine 3x, and we're going to write the 1 over x down here on the bottom. So we'll write the x like that. Now we are going to evaluate this right-hand side. We're going to let x go to 0, so this is 5 times natural log cosine of 0 is 1, and then we have a 0 on the bottom. Natural log of 1 is 0, so we get 0 over 0, and this is the indeterminate form that allows us to use L'Hopital's rule. So now we're going to use L'Hopital's rule. This is the limit as x goes to 0. We have 5 times the derivative of the natural log. That is 1 divided by what's inside the natural log, which is cosine 3x, times the derivative of what's inside, which is a minus 3 sine 3x. And we divide all of this by the derivative of x, which is 1. Let's go ahead and let's simplify this. This is the limit as x goes to 0 minus 15, and we have a sine over a cosine, so that is tangent of 3x. Now we can let x be equal to 0, so we have minus 15 times tangent of 0, which is 0, and this gives us 0. Now, here's where you have to be super careful. You are not done. That just tells us that the limit as x goes to 0 of the natural log of y is equal to 0. But we want to find what y is equal to. So we have to write that y is equal to e to the 0. We're just solving this equation right here. And this is equal to 1. So our limit is equal to 1. In this optimization problem, we're finding the largest possible volume of a box with a square base and an open top. The first step in solving this problem is to read through the problem carefully and figure out what information we're given and what we're asked to find. We're told that if 1,200 centimeters squared of material is available to make a box with a square base and an open top, we want to find the largest possible volume of the box. The second step is to fill in each of these 4 categories using the information from our problem. I went ahead and drew a box with a square base. Now what we have to do is label the sides. If it has a square base, this length and this length can both be x, and then we'll let this height be y. So let's write down that x is our length and our width. You always want to write down what the variables are. And then y is our height. Now let's write down our equation. Our equation is going to relate the variables from our diagram to the information that we're given. So let's look back up. In our problem, it says that we have 1,200 centimeters squared of material. So that means the base, the sides, and the top has to equal 1,200 centimeters squared. So let's write down that we have a surface area of 1,200 centimeters squared. And then let's also write down what our surface area is. It's equal to the base, which is x squared. And then it's equal to all 4 sides. And those 4 sides are the same. So we're just going to have 4xy. So our equation is going to be x squared plus 4xy is equal to 1,200. We'll leave out the units for right now. Now let's go ahead and find if we are going to maximize or minimize a quantity. Going back up to the problem, it says we are to find the largest possible volume. That means that we're going to maximize the volume. So let's write down what the volume is. The volume of our box is the length times the width times the height. So that is x squared times y. Now we need to put our volume in terms of one variable. So we need to come back to our original equation right here, and we need to solve for y. So let's go ahead and let's do that. We have 4xy is 1200 minus x squared, and that gives y is equal to 1200 minus x squared, all divided by 4x. Now let's take that and put it back up into our equation for v. So we have x squared times 1200 minus x squared, all divided by 4x. Looks like one of the x's is going to cancel. So we end up with 1/4 x times 1200 minus x squared. Let's go ahead and let's multiply this through. So we have our v is equal to 300x minus 1/4 x cubed. And we are going to need that, so I'm going to go ahead and highlight that. Now let's think about our domain. We are not told how big the length and the width of our box can be, but we do know that it can't be 0 and it can't be negative. So we're going to say that our domain is x is greater than 0, and let's just make a note that this is an open domain. We'll need that in just a few minutes. Our third step is to take the derivative of our volume and find its critical points. I'm going to go ahead and rewrite our equation for our volume. It is 300x minus 1/4 x cubed. Now let's go ahead and let's take the derivative. Our derivative is 300 minus 3/4 x squared, and we're going to set that equal to 0. So we have 300 is equal to 3/4 x squared. If we multiply by 4 and divide by 3, we are going to get, 1200 divided by 3 is equal to x squared. So this tells us that x squared is 400. And we take the square root of that, and it's really nice. And we get that x is equal to 20. Now we need to put units. Let's go back up. We have centimeters squared for surface area, so x is 20 centimeters. And we'll go ahead and highlight that. Now we need to find y. Our equation for y is right here. So let's use that. Y is equal to 1200 minus x, which is now 20. So we have 20 squared, all divided by 4 times 20. Let's see. This is 1200 minus 400. So this is 800 divided by 80. So we get that y is equal to 10 centimeters. Now what we need to do is find our maximum volume. So let's write down our equation for v. Let's see, we can pick two of them. V is x squared y right here, or the one we have below that. Let's use the x squared y. That one's going to be easier. So v is x squared times y. X is 20, so this is 20 centimeters squared. Y is 10 centimeters. So let's see, this is 400 times 10, so this gives us 4,000 centimeters cubed. Now, it may seem that we're done, but we're not. Our next step is to justify that the answer that we got is a maximum. Our interval is an open interval, so we can use the first derivative test or the second derivative test. Let me go ahead and let's highlight our derivative. there's our derivative right there. That derivative is pretty easy, so I think it's going to be easiest to use the second derivative test. So let's write that down. We're going to use the second derivative test. It would not be wrong to use the first derivative test. It would just be a little bit harder. And let me go ahead and write down here what our first derivative is, so we can then take the second derivative. Let's go ahead and let's find v double prime. It is equal to minus 6 over 4x, which is minus 3/2 x. Now we're going to substitute in that x is equal to 20 centimeters. So we'll say v double prime at 20 is minus 3/2 times 20. And this is minus 30, and it's less than 0. We really don't care what the number is. We just need to know if it's positive or negative. Because it's negative, our function is concave down, and we have a max. We can then say that we have a max at x is equal to 20 centimeters. And then we can also say that v is equal to 4,000 centimeters cubed is a maximum. Now we just have one more step. That step is to reread the problem and then clearly state our final answer in a complete sentence. Let's go back up and look at our problem. Our problem says to find the largest possible volume. So that's what we need to state. So we're going to write down that the largest possible volume is 4,000 centimeters cubed. And that's our final answer. In this optimization problem, we're finding the largest rectangle that can fit inside a right triangle. The first thing we want to do in solving this problem is to read the problem carefully, figure out what information we've been given, and then what we're asked to find. Our problem tells us that we are to find the area of the largest rectangle that can be inscribed in a right triangle with legs of length 3 centimeters and 4 centimeters if two sides of the rectangle lie along the legs. What we want to do now is fill in all 4 of these categories that I've listed here. And notice that I have already drawn our picture just to make things easier. We have a right triangle, and inscribed in our right triangle is a rectangle, and it has legs of length 3 centimeters. So this distance here is 3 centimeters and 4 centimeters. So this distance here is 4 centimeters. Now what we want to do is assign variables. Our variables need to be related to what we want to find. We want to find the area of our rectangle here in red. So we need to make our variables the width and height of our rectangle. So I'm going to let this distance be x and this be y. So let's write that down. X is the width of our rectangle, and then y is the height of our rectangle. Our second category is titled equation. What we need to do for this is we need to find an equation that relates x to y. I think this one is difficult, and a lot of students struggle with this. So let me tell you exactly how we're going to do this. To find the equation that relates x and y, we're going to use similar triangles. If you've studied related rates, you might remember doing this when you had water going into a cone. Now what we're going to do is we're going to compare the sides of our two triangles. So let me go ahead and let me highlight our second triangle. This right here is our second triangle, and it has a leg of x, and then this distance right here is 3 minus y. So using similar triangles, we can say that 3 is to 4 as 3 minus y is to x. Let's put that in our pocket for a minute and we'll come back to it. Let's now move on to what we want to maximize or minimize. We want to find the area of the largest rectangle. So that means that we are going to maximize the area of the rectangle. So we need to write down the formula for that area. The formula for the area of our rectangle is x times y. And now we need to get this formula for a just in terms of x. So we're going to go back to our equation and we're going to solve this for y. Let's go ahead and let's cross multiply. This gives us 3x is equal to 12 minus 4y. So we can say that 4y is equal to 12 minus 3x, and y is equal to 12 minus 3x, all divided by 4. Let's now go ahead and substitute that in for our area. A is now x times 12 minus 3x, all divided by 4. What we're going to do in step 3 is to take the derivative of a so that we can find its critical values. And it makes it easier to take the derivative if we write a in the simplest form possible. So I'm going to rewrite this, and I'm going to say that a is equal to 12 over 4, which is 3. So we have 3x minus 3/4 x squared. Then we can take the derivative easily without having to use the product rule. The last category that we have to fill out is the domain. Let's go back here and look at our diagram. The domain is in terms of x, and x can be between this point and this point. So we can say that x is between 0 and 4, and this is a closed interval. So I'm going to put that down because that's going to make a difference to us in a few minutes. For step 3, we want to take the derivative of our area function and find its critical values, and then find the maximum value of a. So let's go ahead and let's rewrite a. A is 3x minus 3/4 x squared. Now we can go ahead and take the derivative. A prime is equal to 3 minus 6 over 4 times x, and we're going to set that equal to 0. So we have 3 is equal to 6 over 4 times x. So this means that 12 over 6 is equal to x. So we can say that x is equal to 2, and we need units with this. So let's go back up. And notice that in our original problem, our links are in terms of centimeters. I guess we did write that down on the diagram. So x is equal to 2 centimeters. Now let's go ahead and let's find y. Here's our equation for y, and that's what we're going to use. So let's say that y is 12 minus 3 times 2, all divided by 4. This is 12 minus 6, which is 6 divided by 4. We can say then that y is equal to 3/2, or 1.5 centimeters. Now what we need to do is find our maximum area. And we have two equations for the area. Let's go back up here and look. We have this equation and this equation. They're the same thing. I think a is equal to xy is going to be a lot easier to use. So let's use that to find what a is. So we'll write down a is x times y. X was 2 centimeters, so this is 2 centimeters. And then Y was 3/2 centimeters. So we get that our area is 3 centimeters squared. It may now feel like we're done, but we're not quite done. What we have to do now is justify that this area that we got is a maximum. And to do that, we have to go back to our domain and see if it's open or closed. This domain is closed, so that means that to justify that our area is a maximum, we have to find A at our endpoints and then compare it to the 3 centimeters squared. To find our area at the endpoints, let's go back up and look at our diagram. At this point on our left, X is equal to 0, and then at this point on our right, Y is equal to 0. We know that our area is equal to X times Y, and we can use that. So A at 0 is going to be 0 because X is 0, and then A at 4 is going to be 0 because Y is 0. And then we have A at our critical point, which is 2 centimeters, is equal to 3 centimeters squared. So this is our maximum area. Now we're almost done. Our last step is to reread our problem and clearly state our final answer in a complete sentence. Let's go back up to our problem. We want to find the area of the largest rectangle. So we have to state what the area is. Let's state that the area of the largest rectangle is 3 centimeters squared. And that's our final answer. That's all for this exam review. I hope it helps you as you prepare for your exam.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.